Imagine an AI processing unit working on a complex task, like recognizing objects in an image. This task requires accessing and modifying shared resources, such as memory or specific hardware components. Now, picture multiple processes trying to access and change these resources simultaneously. Thread safety ensures that multiple processes can access shared resources without causing conflicts or corrupting data. In the world of AI kernel drivers, which are essential for communication between your AI hardware and software, thread safety becomes even more critical. Understanding how thread safety is achieved in AI kernel drivers is essential for anyone working with AI systems. One of the most common tools used to achieve thread safety is the mutex lock, which stands for mutual exclusion lock. Think of a mutex lock as a restroom with a single occupancy sign. When a process needs to access a shared resource, it first tries to acquire the mutex lock associated with that resource. If the lock is free, the process acquires the lock and proceeds to use the resource. Once the first process is finished with the resource, it releases the lock, allowing the waiting process to acquire it and proceed. This mechanism ensures that only one process can access the shared resource at any given time, preventing conflicts and data corruption. Without proper synchronization mechanisms like mutex locks, multi-threaded applications become susceptible to a notorious problem known as race conditions. Imagine two processes trying to update the same variable simultaneously. Process A wants to increment it by 1, while process B intends to double it. If both processes read the value simultaneously and perform their operations without any synchronization, the final result becomes unpredictable. Depending on which process writes back to the variable last, the final value could be either 11 or 20, leading to inconsistent and potentially disastrous outcomes. Preventing race conditions is paramount for ensuring the reliability and predictability of AI kernel drivers. AI kernel drivers utilize mutex locks extensively to safeguard shared resources from the perils of race conditions. These resources can include hardware registers, data buffers, or internal data structures used by the driver. By strategically placing mutex locks around critical sections of code, developers can ensure that only one process can execute that specific code block at a time. For example, if an AI kernel driver needs to update the parameters of a hardware accelerator, it would acquire a mutex lock before accessing the relevant registers. Once the parameters are updated, the driver releases the lock, allowing other processes to access and modify the same registers safely. This meticulous use of mutex locks ensures that operations on shared resources occur in a controlled and predictable manner. Let's consider a real-world example to illustrate how mutex locks ensure thread safety in an AI kernel driver. Imagine a driver responsible for managing a specialized AI accelerator used for image recognition tasks. Multiple applications running on your system might want to utilize this accelerator simultaneously. Without proper synchronization, these concurrent requests could lead to chaos. For instance, one application might start loading a model while another is already using the accelerator, leading to unpredictable behavior or system crashes. To prevent such scenarios, the AI kernel driver would use a mutex lock to protect access to the accelerator. When an application wants to use the accelerator, it requests access through the driver. This simple yet effective mechanism ensures that only one application can access and utilize the AI accelerator at any given time, preventing conflicts and ensuring the stability of your AI system. In the world of AI, where multiple processes often need to access and manipulate shared resources concurrently, ensuring thread safety is paramount. AI kernel drivers, responsible for managing these interactions at a low level, rely heavily on mechanisms like mutex locks to achieve this critical goal. By carefully controlling access to shared resources, mutex locks prevent race conditions, those insidious bugs that can lead to unpredictable behavior and system instability. Understanding the importance of thread safety and the role of mutex locks is crucial for anyone working with AI systems. Ensuring the reliability, predictability, and overall integrity of your AI applications is essential.